Hi, I'm David Muir, the staff scientist responsible for the Ideas Beamline here at the Canadian Light Source. This video will be a tour of the Beamline's optics hutches and experimental end station. This is the entrance to the experimental hutch, which we call the secondary optical enclosure, or SOE. It is secured by an access control interlock system which prevents the X-ray shutters from being opened unless a lockup procedure has been completed, ensuring that no one is still inside. Inside this hutch is where the samples are mounted, and where you will find the instrumentation to analyze them using the X-rays produced by the synchrotron. It is located at the end of the beamline, so we cleverly call it an end station. We'll have a closer look at the end station on the way back out. At the back of the hutch is the entrance to the primary optical enclosure, which is also secured with an access control interlock system. This hutch contains all of the equipment and instrumentation required to bring the X-rays generated by the synchrotron to the experimental end station. For a number of reasons, the flight path of the X-rays must be maintained under extremely good vacuum. Much of the equipment that you see here is for maintaining that vacuum within the stainless steel spools that make up the flight path. On the other side of that concrete wall is a storage ring where relativistic electrons are orbiting. Those electrons emit X-rays as they are accelerated around corners by magnets. This beamline uses the X-rays generated by one of those bending magnets. Because the electrons can be knocked off course by gas molecules, the vacuum in the storage ring must be exceptionally good. Because the beamline is connected directly to the storage ring, the vacuum at this end must be exceptionally good as well. The pressure here is as low as 10 to the minus 11 torr, or nearly a million billion times lower than atmospheric pressure. At pressures this low, the remaining gases are not fluids, but instead behave more like ping pong balls, bouncing around the system at random, so it's not possible to suck them out. The pressure is maintained by using ion pumps like this one, and this one. These pumps work by creating an electric field potential of several thousand volts, which ionizes any gas molecules that wander into them, and then trapping those ionized molecules by burying them in titanium plates. As we move further down the beamline, we no longer require such exceptional vacuum. Here, the vacuum is required to prevent air from absorbing the photons before they can reach the experiment, and to keep the optics clean. Pressures around 10 to the minus 8 or 10 to the minus 7 torr are adequate, so we use different types of pumps at this end, like this turbomolecular pump. They operate much like high-speed turbines, knocking the gas molecules into the back end of the pump, where they collect until there are enough of them to behave like a fluid again. From there, a scroll pump, which isn't a lot different than your vacuum cleaner, is used to suck them out of the system. In addition to the pumps, gauges like these are used to monitor the pressure in every vacuum section at all times. The beamline is divided into vacuum sections by gate valves like these. This makes maintenance easier and provides protection in the event of a leak. These red and blue tubes provide cooling water to some of the optical components in the beamline that are exposed directly to the synchrotron light. There is a large amount of power in the beam, and since the optics are mounted in vacuum, there is no convection and very little conduction to remove heat from the system. Without water cooling, the light from the synchrotron would destroy these components. The first of these components are the white beam slits. They're a set of 4 water-cooled blades that can be moved in position to crop the beam as needed and to block out any unwanted scatter. The next optical component is the mirror, which can collimate or focus the light onto the sample as needed. It is a 60 cm long precision polished silicon mirror with a rhodium coating. It has a 6 cm radius to focus the beam horizontally and is installed in a bender mechanism that can be used to adjust the focus vertically by bending the mirror to a radius of a few kilometers. The mirror faces down and is aligned so that the X-rays reflect off the mirror at a very shallow angle, which is necessary so that the mirror does not absorb them. Further down the beamline is the diagnostic screen. It is a water-cooled aluminum block with a phosphor embedded in it. It can be lowered into the path of the beam so that the beam's profile is visible to a camera. This provides important information for aligning the beamline optics. After the diagnostic screen is the double crystal monochromator. This device allows us to select the specific energy or wavelength of light that we require for a particular measurement. It does this using a pair of diffraction crystals. The light from the synchrotron diffracts off of the crystal, constructive interference allowing only certain energies to continue on, determined by which crystal and the angle the light strikes it at. A second crystal rotates along with the first crystal, and translates up and down to keep the resulting beam parallel and at a constant height. The last component in the PoE is the safety shutter, which is a large tungsten block that can be dropped into the beam path to prevent any X-rays from entering the SOE, making it safe to work in that hutch. The SOE contains a variety of equipment and instrumentation that can be used to analyze samples in several different ways using the light from the synchrotron. Just inside the hutch is a second set of 4 jaws that can be used to crop the beam down to the size required for a particular measurement. Next, there is an ion chamber, used to monitor the intensity of the light being supplied by the beamline. It works by using high voltage to collect the ionized gas molecules produced as the X-rays pass through. Next, we have a vacuum chamber that samples can be mounted in when needed. Removing the air around a sample can be beneficial for certain types of measurements. Here is a 2-dimensional motion platform that samples can be mounted on. It can accommodate larger samples or a larger number of samples than the vacuum chamber, and is easier to work with if a vacuum is not required. In addition, it can be used to scan the beam across the sample in 2 dimensions to produce elemental distribution maps. A second ion chamber after the sample monitors the amount of light that passes through the sample. By measuring this at different energies, we can learn about the chemical speciation and bonding environment of various elements in the sample. A third ion chamber is used to monitor the signal from a reference standard, allowing us to calibrate the data as it comes in. Finally, we have the silicon drift detector, which is an energy discriminating photon counting detector. It works by measuring the amount of charge deposited in a silicon chip by every photon that strikes it. By analyzing this charge pulse, the detector can determine how much energy the photon had. By measuring the energy distribution of photons emitted by the sample when the sample is excited by X-rays from the synchrotron, we can learn about the elements present in the sample as well as their chemical state. The IDEA's SOE has a significant amount of free space. This allows us to bring in additional equipment and instrumentation for testing, development, and unique experiments. This concludes our tour of the IDEA's Beamline. Thank you for watching.